Great. No. Okay, let's start our next session. This is composition, volatiles, and outbursts. Our first talk will be from James Gerbs Bauer, talking about NEOWISE carbon monoxide and carbon dioxide observations of active centaurs. You have 15 minutes all talks. We have 4 talks, all of them 15 minutes total. So 12 minutes plus 3 minutes questions.
Great. Thank you, Mike. So thank you for being here, and thank you for the organizers for having this symposium workshop. I just want to start off by thanking also my co-authors, a large list here, and remember that this is a team effort. I'm going to concentrate mostly on NEOWISE results, although I want to point out that Spitzer is also doing some similar work in terms of CO and CO2 measurements in very similar fashions through broadband. So just to remind everyone some of the salient features of the NEOWISE mission. It started off as an augmentation to the WISE spacecraft, the Wide Field Infrared Survey Explorer mission. It uses the WISE spacecraft to look at and characterize, to discover and characterize near-Earth objects primarily. And it has, during the cryogenic mission, which lasted through August, from January of 2010 through August and September of 2010, most of these channels were active 3.4, 4.6, 12, and 22 microns. After the cryogen ran out, only the 3.4 and 4.6 micron channels were active, and the spacecraft was turned off and put into hibernation in February of 2011. Chelyabinsk happened. The spacecraft was turned back on in December of 2013, and it's been going ever since. It's almost to December, or actually, if it makes to November, it will be a decade of NEOWISE observations. So, just to kind of highlight some of the non-CO or CO2 characteristics observed by NEOWISE, and to kind of establish the connections between centaurs and comets in terms of the observational parallels. There is a color albedo relationship between centaurs. The bluer objects, the more neutrally reflected objects, tend to be darker and have mean albedos clustered around a few percent, similar to comets. This comes from the NEOWISE survey, which surveyed 49 true centaurs, if you will. And if we look at the red populations, those tend to be brighter. Also, if we look at the thermal fits from the cryogenic mission, there's a term that the near-Earth asteroid thermal model uses called a beaming parameter that sweeps in a lot of different parameters into that. But one thing is that a beaming parameter close to 1 is is consistent, more or less, with a low thermal inertia object. And so the beaming parameters for centaurs and Jupiter family comets alike are close to 1, close to unity. A lot of these results were actually determined also with Spitzer, and particularly for the JFCs with Jan Fernandez SEPCON survey, and for the with the Spitzer Centaur survey, this relationship was first suggested by the work by Stansberry et al. in 2007. That, by the way, I misquoted. TNOs are cool. Yesterday for diameters, I think a better reference for centaurs would be that paper, 2007 Stansberry et al. in terms of other relationships, when we look at the size distributions, we look at the sizes on the order of 10 kilometers or larger for the Centaurs that were observed by NEOWISE in the cryogenic mission, and compare them with the cumulative size distribution slopes. Compare those with the Jupiter family comets. They're comparable and not comparable with what was seen for the long period comet cumulative size distribution slope. And again, our results from for the comets at least are similar to those in the literature, and I think also the Centaurs for some other size surveys. So if we start, so there are a lot of observational parallels between the Centaurs and the Jupiter family comets. We know that. It's not, maybe not surprising, since there is a lot of dynamical evidence for the populations evolving, for the JFCs evolving from the Centaurs. But one thing, that's I think of particular importance is where things start to break down, and where the relationships don't really map very well. So comets that are the Jupiter family comets we see are down to on the order of a kilometer up to a few tens of kilometers in size. For Centaurs that we observe, actually, they're on the order of a few tens of kilometers up to a few 100 kilometers in size. In terms of activity, active Centaurs tend to come within Saturn distances, although this is not totally true, or not totally, it doesn't totally hold up. And then, but if we assume at any Centaur distance, water is basically not active here. It is not really active at distances of close to 5 AU. It's not really a driver of activity, but CO and CO2 are. And if we scale the production rates by the areas and the predicted production per area, we should expect something like 50 to 100 times as much CO at 15 AU as we would see of water for JFCs at 3 AU. And for CO2, again, 50 to 100 times as much at 6 AU. And we don't. So this model does not really map very well, just scaling for the Centaur populations. So scaling from behavior from comets do not really work very well with Centaurs.
So can you clarify, we're not seeing enough?
We're not seeing that high, correct. Okay. So how do we know this? How do we know how much CO2 is produced? Well, some very good observations are made in the submillimeter, and those will be discussed later, later today or later in this session. There's also spectral observations of the 4 to 4.5 to 5, between the 4 and 5 micron region of CO2 and CO. And spectroscopically, as with Akari, these can be discerned individually, and the production rates can be derived individually, along with, for example, other species like water. But that's not the case for the NEOWISE band, which covers from about 4 to 5 microns. And that's also true with the Spitzer bands as well. So when we see CO or CO2 productions, it's exactly that. It's CO or CO2. We can't differentiate between them except by using what we think would be most active or most dominant in a given situation. Or if we couple the observations with submillimeter or other spectroscopic observations that constrain the CO. But moving forward, what we're forced to do then is to provide some kind of a way of assessing the CO and the CO2 combined production, so we convert everything, just for the sake of comparison, into CO2 rates, assuming the efficiencies of the CO2 emission. just for comparison. And when we do that, and we divide it by the dust production ratios, we see some interesting trends. Out to about 4 AU, the behavior of the CO2 rates, proxy rates, relative to water, or relative to the dust, behaves similar to what we would see for water production relative to the dust. And beyond it, we actually see a different behavior, a different regime. Both long period and short period comets tend to be roughly equivalent in terms of distances from 4 AU and their distributions. But when you get beyond it, the activity tends to be dominated by long period comets, with one notable exception here, by the way, and that's the active Centaur 29P. This actually bears up it continues. This is affirmed by the NEOWISE reactivation mission data too. These are just from the first 2 years, and we see that the activity is actually broader out to more extended at larger distances with the long period comet population.
Can I interrupt you just for a second? I don't know. But can I switch microphones?
1 minute left. Oh, great.
Can I switch microphones with you really quickly?
Oh, sure.
Yeah,
okay.
That one's having a little bit of static.
All right. That's okay. So NEOWISE has actually observed a lot of all of the active Centaurs. It's observed all of the active Centaurs, but hasn't detected all of the active Centaurs. These are the ones that it has detected, minus 1 or 2 points that have not quite been reduced. Mea culpa. This is preliminary work, but these are primarily from Echeclus near the bottom of the graph. These right here are primarily from Chiron, and then up at the top, it's primarily from Swashman-Wachman 1. We can look at that a different way, and these kind of pull apart a little better. Chiron, Echeclus, and SW1. And when we look at our activity, since we only have a minute, I'll rush through these slides. We see that's very variable, but often present for Echeclus. By the way, this is not an outburst here. This is a star in the background. Sometimes for Chiron, but less often in terms of when we observe it versus when we actually detect it. Believe it or not, there is kind of a faint detection here. It doesn't show up very well, but. But for SW1, it's rare that it is not detectable by us. It's even detectable in here, which is a very noisy region. These two here, second row, at the end of the second row, those actually have central points that are detections. However, the next two do not. And that's the only set that we do not see SW1 in. Okay, so what do we need for further work? We need a more sensitive instrument. NEOWISE, just in terms of diameters, more or less detects at about 8 AU on the order of 20-kilometer objects, for example. However, help is on the way with NEOCAM, which will actually detect on the order of kilometers in size. So down at 8 kilometers distance. So it'll be able to probe a lot of the Centaurs, and that's diameters, not radii. A lot more of the Centaurs. It'll also be more sensitive and be able to detect CO or CO2. It'll have a similar band as NEOWISE, but be about 10 times more sensitive. So I guess that's all I have. And let me just, one more thing. Because of its extended, you've already seen this anyway, but because of its capabilities, we're going to need bigger plots. Okay. And those are my conclusions. And that's it.
Thanks.
Thank you.
All right, questions for Gerb's talk? Yes.
Yay. Could you talk a little bit about SphereX?
What's that?
Could you talk a little bit about SphereX?
Okay, so SphereX is a mission that's very similar in its approach to NEOWISE in terms of its survey strategy. So again, at about elongations of 90 degrees, if I'm not mistaken, it will passively look at the sky and obtain actual broad or low resolution spectra, but of sufficient resolution to separate the CO and the CO2. And whatever is accessible to NEOWISE, that's about the sensitivities that you should see with SphereX. So that'll be very exciting. You will be able to get separate CO and CO2 abundances from SphereX. And in some sense, have some, like NEOWISE, have some way of debiasing your populations because it won't be affected by weather or other conditions. Although I don't know how much submillimeter really is affected by weather. But okay, all right, we don't want to know. Okay, great. And I guess, yeah. Does that answer your question? Yeah.
Another one for Gerbs. Excellent. Yeah. All right.
I'm just going to add this then. These are some questions for later topics to discuss and consider. I don't know if we do it now or later, but we can do it later.
We do it later.
Yep.
Excellent. Thank you.
Thank you.
Okay, our next talk is online. Next talk's online. Casper Wierzchos. Is he ready?
Yeah.
Okay. This talk is characterizing outgassing in Centaurs.
What would the name be? Oh, I see.
Hello?
Yes.
Do you hear me?
Yeah.
Oh, great. How do I go back and forth on the slides?
Yeah, you tell me and I will advance the slides. So.
Oh, great. I will just say next, I guess.
Can you see, how can I signal?
I see everything really, really good, like the screen and everything.
Okay, good. So I'll try to signal you at 10 minutes, at 10 minutes, and then at 12 minutes when there's 0 time left.
Great, thank you. Well, hello everybody from Tucson. I don't think you guys can see me. I see you. So I will be talking about characterizing outgassing in Centaurs, and mainly in the submillimeter and millimeter range. And why in that range? Well, next, please. Thanks. It has to do a lot with what Gerbs just said. So first of all, let me start saying that the portion of active centaurs relative to the total centaur population is very, very small. And the activity that we see in those centaurs has to be driven by something other than water ice sublimation. As we know, water ice sublimation is the primary volatile component of comets, but at heliocentric distances of less than 3 to 4 astronomical units, water ice can just, at heliocentric distances further away than 3 to 4 astronomical units, water ice cannot be the cause of activity, because if its sublimation temperature is too high. So a substance with a much lower sublimation temperature, what we refer to as a super volatile or a hyper volatile, for example, carbon monoxide or carbon dioxide, must be the source of activity. Now, it's interesting to note that carbon monoxide has been observed in many distantly active comets, that is, comets that have exhibited activity up to 10 astronomical units, if I'm not mistaken, with in the case of Hale-Bopp, and several other comets in the range of 6 to 7 astronomical units. So we think that carbon monoxide must be, if not the full responsible to some degree of the activity of not only distant comets, but also Centaurs, because interestingly, carbon monoxide has been observed in 3 Centaurs so far. Next. So obviously the most enigmatic and strange is 29P. This Centaur with an almost circular orbit was the first one in which carbon monoxide was detected. It was in 1994 by Senna and Jewett. And what's interesting about this object, like Gerb said, is that it's observed to be active to some degree, but also if you look at its carbon monoxide production rate or its carbon monoxide emission, it always has CO. And it varies quite a bit, by approximately by a factor of 3. No matter when you look at 29P, it's going to have a carbon monoxide production rate ranging between 3 to 9 times 10 to the molecules per second. Here we just have a nice picture of 29P outbursting. And on the right side, I believe this is the first detection of CO in 29P by Snee and Jewett. So at USF, Maria and I, we've been following and observing 29P with the Arizona 10-meter SMT since 2016. And next slide, please. Thanks. And we were able to make a series of plots where we basically plot either the heliocentric magnitude of this object, that is the magnitude corrected for geocentric distance, which very, very well correlates with AFRO, basically, plotted against carbon monoxide production rate measured by us with the ARO 10-meter SMT at the millimeter range. So in this plot, for example, we have the evolution of the magnitude of the heliocentric magnitude of 29P between February 2016 and May 2016. So as we see in the black dots, that is the magnitude of the object, and 29P had one of its famous outbursts in mid-March 2016. What's interesting is that before that outburst, when 29P was in its known as its quiescent stage, in which it has a low level of activity, we observed what appears to be a CO outburst, where CO grew quite significantly, but this did not have any counterpart in the activity of the comet observed in invisible wavelengths. Also later on, we see here after the dust outburst that carbon monoxide appears to go down, then goes up again. And in conclusion, it doesn't appear so far to be correlated. So this is a part of a work in progress. We have measurements of this kind through 2018 and early 2019, and we're still analyzing and trying to find a way of maybe correlating or see what is going on, because it appears that the relationship between the CO emission and the dust activity in this comet is not well understood. Next slide, please. Thank you. Another strange Centaur is 174P Echeclus, which also has outbursts, but not nearly at the same frequency as 29P. As a nice active Centaur, it's also big, it's large, it has a diameter of around 65 kilometers. And about, I believe, 6 episodes of activity has been observed since its discovery in the year 2000. And the strangest one was perhaps in 2005, where the source of activity detached from the nucleus of Echeclus and appeared to be trailing behind the nucleus, as we can see in this image in the lower left corner, obtained by Philippe Rousselot with the VLT. So we see Echeclus, it's the dot, the point source at the nucleus of Echeclus, and the source of activity was this sort of field of debris, perhaps, that was trailing behind the nucleus. So in 2016, due to the fact that Echeclus was very close to perihelion, we decided to look for CO with the ARO 10-meter SMT, and we got very weak detection of carbon monoxide, the spectra is at the lower right. And we derived a carbon monoxide production rate of 7.7 times 10 to the 26 molecules per second at a heliocentric distance of 6 AU. That is a factor of 2 less than for 29P. And it's also interesting to note that it has a much lower carbon monoxide output and also has a lower frequency of outbursts compared to 29P. Next slide, please. So other active centaurs notable are also 95P Chiron that GURPS mentioned. And this is the third centaur in which CO was detected by Maria and Alan Stern back in the 90s. And this object also exhibits episodes of transient activity, although much less common than 29P or 174P. Now, there are other objects, other active centaurs, but they have not had carbon monoxide detection so far, maybe because no one has looked for it. I know that people have looked into some of them and were able to establish upper limits of carbon monoxide production rate, but there's definitely work to be done in this direction. Next one, please. So this is a plot from our paper from 2017, in which we basically plotted what we call the specific production rate, which is the carbon monoxide production rate divided by the diameter of those objects. The diameter was obtained, I believe, from the work of Stansbury. And we also plotted it against the heliocentric distance. Now, if we assume that centers at comets have, to a certain degree, similar chemical and physical characteristics, we can plot, then their carbon monoxide production rate should scale commensurate with surface area and distance from the sun. And what we also did is we plotted the specific carbon monoxide production rate of Hale-Bopp to compare it with these centaurs, because we use Hale-Bopp as a proxy for a non-processed comet. So what we see here is basically that, with the exception of 29P, centaurs appear to be very, very CO depleted. We see that Echeclus, Chiron are around 10, a little bit more than 10 times depleted, CO depleted compared to Hale-Bopp. And we see all these other purple triangles in the plot. Those are upper limits, upper CO limits obtained by Michał Drachus, published in 2017, that we included in this plot, just to make the point that centaurs, they appear to be very CO depleted. Even though they didn't get detections, sometimes they basically fall under the Hale-Bopp straight line, of course, with the exception of 28P. Next one, please.
2 minutes left.
Yes, it's the last slide. Next, please. Thank you. So, open question. Is activity in centaurs common but too weak to be readily detected? Now, are some other centaurs being active, but we just don't know because either no one has looked or no one has analyzed, or that data is basically in some Pan-STARRS repository and no one has data mined it and we don't know. What is the contribution of CO2 to the activity of these centaurs? For this see the next talk by Olga Harrington. And also some very interesting questions. What is causing the outbursts of 29P? And what's even crazier, what is the relationship of the hypervolatile carbon monoxide with the dust in this center? And that's it. Thank you. Any questions? Thank you.
All right, questions for Casper? Throw it now.
Okay, Alan Stern, Southwest. If we could go back one slide where you talked about the depletion of CO in most centaurs. Could you put that in another context? Is it, my question is really about whether relative to comets, the centaurs are CO depleted or 29P is CO enriched?
Yeah, it's very difficult to draw any conclusions also from what is such a small sample, because let's remember that we only have 3 centers where carbon monoxide has been detected. 29P seems to be, I guess, an exception in many ways. What we did basically is compare it to HALE-BOP, only because it has a lot of CO measurements, and it works for us as a proxy for a non-processed comet. So basically, yes, to answer your questions, centers appear to be C depleted compared to HALE-BOP and to other long period comets, for that matter, where CO has been detected in them.
I would think a better comparison is to short period comets that come from the same population, the scattered disk.
Oldest top.
You want it?
Yeah.
Yeah, Olga will approach that topic. I think it's worth making the point with whenever you have 29P on a plot like this, that we kept the outbursting data on here, and we might want to think about as a group whether we should look at the quiescent state for this comet, Centaur, but also Holmes. When we brought up Holmes, does it make sense to look at the amount of CO Holmes was outputting before the outburst, when we talk about how much CO does Holmes have, or how much CO does 29P have? Do you really want to look at the outbursting number or the quiescent? I think that's something we should discuss.
Yeah.
Matthew Knight, University of Maryland. First question is very simple. What's the date on this plot? On the bottom right, it's blocked in our room. 2017.
Yeah, this was published in our paper from 2017. Yeah.
Okay, great. Then paper's in my backpack now. The other thing I just want to say on this plot, I'd be interested, maybe this will come up in Olga's, but since HALE-BOP is weird from the standpoint of being a very dusty comet, it might not be the right comet to be using as the normalization, although I realize it is the comet where we have all these observations. But
yeah,
that could change the relative answer of what is abundant or not abundant.
Yeah, sea observations along carbon monoxide observations along such large heliocentric distances are very sparse, and HALE-BOP was observed by so many groups. There's so much data that it was kind of like the natural fit to compare it. I can think maybe HALE-BOP has also a lot of observations, but doesn't come nearly close enough to the amount that HALE-BOP had. But yeah, I agree that.
Yeah, online.
Comment online from Dennis Bodowitz. Ahern et al. 2012 found that CO H2O abundances span 2 orders of magnitude, and HB will be on the high side.
Okay.
Yeah, Jordan.
All right, so this is to follow up on Maria's comment, following up on someone else's comment. So let's just all rewind the tape a little bit. I think it would actually make a lot of sense if this is just outburst activity on this plot for 29P. If we understood what the quiescent CO production was, that might be telling us a lot about what actually might be driving these outbursts.
Now, we have been following the CO production rate of 29P since 2016 in many days, over consecutive days. And so far, this is related to that plot that I showed of magnitude versus CO in 29P. I can tell you that it's very difficult to draw any conclusions. Basically, you see the carbon monoxide rate of production rate of 29P sometimes double from day to day, whereas nothing happens in the dust or invisible wavelengths. Sometimes even triple from day to day, and it's like, okay, why is it 3 times higher today than yesterday? The comet is not going through a dust outburst. What is going on? So yes, I agree, but it's very difficult to establish what is a quiescent state in 29P in terms of CO.
Can you say that for discussion?
Okay, so just a comment, and I'm harping on what I've said before. These are COs that we measure in the coma, so in the activity. These are not necessarily the CO levels in the body itself. And so if I'll draw the Rosetta comparison again. Rosetta had a lot of very short-term variability that was dependent on specific structure, composition, nucleus facets, things like that. And so the differences in the CO might not represent necessarily original depletion, but we might be looking at different kind of localized activation that show up as different CO activity levels. So, for example, Chiron might not be exactly the same kind of CO activity as 29P shows.
Yeah.
Great. Let's thank Casper one more time.
Thank you.
Ready for, yeah, you got results right here.
Can I close that?
Yeah, go ahead.
Okay.
Thank you.
You could try using this one again.
Okay. That's the talk. Okay, our next talk is by Olga Pinto, CO and CO2 abundances and centaurs, comparisons with Oort cloud comets and Jupiter family comets and future directions. I'll give you a 2-minute and 0-minute warning. Yeah.
Okay. So as Mike said, I'm Olga Harrington Pinto, and today I will be talking about the production rates of CO, CO2, and comparing it to some of the surface areas within different types of comets as well as centaurs. So in the first graph that I have right here, I'm looking at the production rate and how it compares to the surface areas of many different types of comets. So as you'll see, a lot of them exhibit different behaviors. At the top, those blue points near the upper dotted line are Hyakutake mostly. Yeah, they're all Hyakutake. And that is just one comet that had a lot of observations made of it. But if you look at other ones, thanks. Thank you. So these points right here are Hyakutake. And it's nice to be able to compare it to Hale-Bopp, but for other comets, we only have 1 point. So it's hard to just say anything decisive about any comet in particular. If we group them by their families, however, we can start to see more of a resonating behavior. So the blue points on the graph are the centaurs, for which there are 6 different centaurs. And the ones that are right here are 29P. The Oort cloud comets are comprised of 2 in particular, Hyakutake and Christensen. And the Halley-type comets are just Comet Halley. And they're the red points right there. And the JFCs, I have 13 of them, and they are mainly in the middle region. So looking at this graph, if we kind of put 29P to the side for a moment, we can see that most of the other centaurs exhibit CO depletion, at least in comparison with Hale-Bopp. And the JFCs seem to show that they are as rich in CO as Hale-Bopp. If we had more data, we would be able to say more about the other comets, but do not. So looking at the JFCs, we can actually say that comparing it to the Hale-Bopp, we have a lot of CO-rich comets, at least comparing it to their surface area. And looking at the centaurs, in this region, there seems to be something that might be turning on CO activity, or perhaps they're just not naturally CO-rich. Then I looked at the CO and the CO2 production rate. All of this is derived from the and the CO and CO2 rates that have been there.
Folks are complaining. Sorry.
That's good. Yes. So if we look at the CO and CO2 within these comets, we can actually see where they're more CO-rich or CO2-rich. So all of the measurements that are here are not ones that have been used with NEOWISE, because the CO and CO2 is detected in the same band, so you can't identify each species individually. But here, all of these measurements have the CO and the CO2 identified separately. So looking at the ones above the upper line, upper dotted line, they're showing a ratio that's greater than 2. And the lower line shows that they're CO2 rich. So it's a ratio of less than 0.5. Looking at the comet families again, the JFCs group together at the lower end for the CO2-rich comets. And remembering from the previous slide, we can say that they are CO-rich, but they're even more CO2-rich, which is really interesting to see in the JFCs. For the Centaur, we have 29P, which is up here. And we have our Oort cloud comets spread out all over the place. So looking at a side-by-side comparison, you can't really say too much in comparison to the Centaurs from both of the graphs. But for the JFCs, we can say that they are more CO2 rich, but they are also very CO rich. Yeah. And some of the questions would be, how can we get more CO2 for Centaurs? Since they're very far out, we would need spacecraft to go out there and look at it and detect it. And from past observations that have been made, is there any way to rectify it so that we can derive CO2 from those measurements? Also, if we got more points, what could that say about the families? So if we had more points for Centaurs in here, would they all behave at this upper end of the spectrum? Or would they start just spreading out all over the place? And yeah, that's it. Any questions? Should I toss it to him?
All right, Jordan Steckloff, PSI. Could you go back to a couple slides where you're showing classes as a function of, yeah. So the Hale-Bopp is an Oort cloud comet, right? Yeah. Yeah. So this plot seems to suggest that Hale-Bopp is a depleted Oort cloud comet relative to the other Oort cloud comets in terms of. Sure. Because otherwise, it's. I mean, so does that suggest that Hale-Bopp is not pristine, or that it's not the best baseline that we should be normalizing against?
I think it's the best baseline because there's the most data available at the moment.
Fair.
If we had more samples, that would be really nice. Because the Oort cloud comets that we have in here, it's essentially Hale-Bopp is all of this, Christensen is right there, and Hale-Bopp is everything.
Right.
So it's really only a comparison between Hale-Bopp and
Right. Well, it is more of a comment. This might relate to the previous talk, that this might suggest that it's not, we can't treat it as effectively pristine material, even if that's the one we have the best data.
You want to go next?
Which one would you actually treat as pristine?
I don't know.
I mean, in general, the language of pristinity for comets is vague, in my opinion. But
Okay, yeah, Alan Stern, swear with another opinion. Oort cloud comets get to be Oort cloud comets because they were orbiting in what we now call the Centaur region, even if that was more compact.
True.
Right? They got to be Oort cloud comets because they suffered a close encounter with a giant planet, and they were thrown up on the lip of the potential well. That's a stochastic process, and each individual comet spends a different amount of resonance time down in this warmer region, losing CO all the time. So you would expect some wide distribution in their CO abundances based upon which ones stuck around longer where it was warm and which ones got ejected earlier. And until we have a large enough sample to really find out where the mean is, 3 points is a good start, but I wouldn't take it too seriously.
Yes, I think I agree.
All right. More questions, more comments, Matthew?
Not on here, but 2016, or I don't think you have it plotted, 2016 R2, would that be way up off the top?
So R2 is in here.
Okay, but what about as on the previous one? Oh, we don't have a radius estimate. Is that the problem?
Yeah.
Okay. So for those of you who are not up on current comets, 2016 R2 is basically tons of CO and no water. It's really weird.
What's really essential distance?
2 to 3.
Does anyone have a diameter for R2?
R2 is actually about this big in the movie.
That's a different.
When you're standing further away from Save. So actually, to follow up on Alan's comment, there is sort of a time constant or a time scale. If these objects spend some time before getting ejected to the Oort cloud, a certain amount of time in this certain range of heliocentric distances, they will deplete their CO to a very similar level, barring very specific, very body specific processes. And so the real difference would be how much time did the object spend before getting tossed to the Oort cloud at what, let's say, annuli away from the sun. That would pretty much depend on how much really initial kind of solar system initial abundance.
By the same token, you'd expect that the scattered disk objects, similar behavior, but they just didn't get ejected, way up on the end of the potential well, right? But in addition, even in the scattered disk locations, for most of them, they can still slowly continue to lose the CO.
Yes, I mean.
So it wouldn't be surprising. Exactly. Right. Right. So you would not. It wouldn't be surprising if new scattered disk objects look depleted, simply because only their surface layer has been depleted over time.
Exactly.
Right. There you go.
Go ahead.
Okay. I mean, that's the basic conundrum of supervolatile species, right? If you see them, it means they were retained in some fashion. But if you see them, it also means that they get activated when you see them. So they have to have a sweet spot where when they were far enough, they were kept there. And when they come close, they get activated. And for supervolatiles, that's pretty much a one-off occurrence. For supervolatiles, for CO, once you get the CO, it's supposed to be lost, and then you can only find it again if you input more energy into the nucleus to find it buried maybe deeper, which I would just circle back to the idea of activity that I think was the hallmark of the day. SW1 is weird. It's really weird. It has CO all the time.
Yeah, good general discussion.
I just want to say a quick.
Yeah. Also, if there's more questions for Olga too.
Yeah, it's focused towards Olga. So, and yeah, no, this is really good work. I wanted to ask you, so the Oort cloud comets, they look like they have this linear relationship, but the Jupiter family comets, can you explain more or less why you might expect them, why they are more dispersed? Do you think it's just because of their insulation, or do you think it's compositional? And this kind of gets at the heart of, is this compositional, or is this, is this primordial, or is this evolutionary?
Wait. Can I throw it?
Okay. I think it depends on the age of them, because some of them have gotten closer to the sun and more times around the sun than others. So that might be why some of them seem more depleted than other ones.
Okay, I hope I didn't miss this, but did you check whether this correlates with the carbon depletion? Okay. The Hearn paper.
Okay.
Yeah.
The water?
Yeah, with the carbon rich and the carbon poor ones. Yeah.
Great, thanks. Thank Olga one more time. All right, our next talk is from Dan Boice. Are Centaurs comets? Well, good question. Yeah, he's online, sorry.
At least he's not here.
Nope. Oh, yep, I guess so.
Cody, is he online?
Yeah, but
Because he wrote me something about perhaps intermittent power or connection.
Oh,
Why? Yeah.
are you there? Can you hear us right? Yeah, I mean, his microphone's connected.
Is he responsive?
Dan, we see you online, but we don't hear you talking.
Oh, hi.
Oh, there you are. Great. All right.
Yep. Can you hear me okay?
Yeah, that's okay. I will advance your slides. Just let me know when. I will also give you a 2-minute and a 0-minute warning. So go right ahead.
Hi, all. Thanks to the organizers for the invitation to present at this workshop. I'm expanding the geographical representation of the workshop because I am in Thailand right now, visiting some in-laws, and well, this gives me one advantage. Captain Marvel has already opened here yesterday.
Spoil it.
So if you're really nice, I may give you some spoilers. But for sure, make sure you stick around for the last post-credit trailers. There's 2 of them. The disadvantage is at least for me, I'm 12 hours ahead of you. So right now it's a little bit past 2 a.m. in the morning. If I start to, slow down or show some signs of being drowsy, please forgive me. Okay, I would like to look at centaurs as bodies that are related to comets and pose the question, are they really comets? Well, you can see by the etching that I have included, which is the Centaur Chiron, it's obvious that centaurs are comets. I mean, you can see obviously there's a tail to the centaur, and the centaur has some kind of activity, is emitting some kind of gases or dust. So therefore, centaurs are comets. Can you advance to the next one? I mean, that may sound a little bit humorous, but that's basically how we define comets these days. We use a very ancient definition of something that appears in the sky to have a tail or to have a surrounding coma, fuzziness, but, and of course, should show some proper motion. But there's really no general definition of a comet. We're using this phenomenological or observational definition from, a couple of thousand years ago. We should be making a distinction between the comet, which is the phenomenon in the sky, and the comet nucleus, which is the actual physical body, and of which we have some very detailed information about now. You can see common dictionary definitions are very much lacking. Why should we worry about this? What's the need for a definition for a comet? Well, of course, that would provide a standardization so that when we talk about comets in the literature, we eliminate ambiguities, avoid confusions, and we can talk about relationships to other solar system bodies. It's also important to convey knowledge to the public in a very clear and standardized fashion. As we gain more information, particularly 20th century, 21st century, it really causes us to go back and revise our understanding of these small solar system bodies. So I think this discussion of what is a comet is very relevant today, particularly since we live in such an exciting time. We're discovering all kinds of interesting small bodies out there, the active asteroids, main belt comets, Trojans, Centaurs, obviously sun crazers. So this I think would be a timely discussion. Go to the next slide, please. Classification schemes, well, the one we're using now, observational, is obviously important, but we should expand it beyond just broom stars or hairy stars with proper motion. Seems like somewhere in the 20th century, latter part of the 20th century, we've kind of informally added to this definition that the activity should be sublimation driven, whether the sublimation is coming from surface ices, supervolatiles from subsurface layers, or even from dust in the coma. We've already heard some very interesting presentations about dynamical aspects of the small bodies, so that should obviously play a role. Physical chemical properties, things such as the size, shapes, bulk properties, compositions, and the like are obviously very important to this discussion, as well as formation or origin scenarios where we talk about the time and place of formation, whether objects might have been moved to different places in the solar system and the like. And of course, probably taking a basket or a combination, all of the above, would be the best approach. Next slide. Well, just to expand a little bit upon these classification schemes, the observational ancient definition that we're using today obviously is an important aspect of comets. We find, as was noted, some time ago, cometary doesn't necessarily mean comets. We have other objects that appear to be comets, but we would not accept them as comets today, leading Messier to make his famous list. Of course, dynamical characteristics such as tesseract parameters, non-gravitational forces, being part of their orbital characteristics. The sources where these may come from also play a part. The next slide, please. Physical properties. Comets that we know of today that we recognize as comets have volatile contents, especially water. They're small, from hundreds of meters to tens of kilometers. They have irregular shapes, low bulk densities, which lead us to the idea that they're very fluffy or porous, low albedos. They have freely expanding atmospheres, extensive exospheres, and we generally note that the activity that we observe from the comets is driven by volatile sublimation. Other things that might be interesting that we don't really know of yet is comets having rings or binary comets, aside from, say, contact binaries. And where would, say, dormant or depleted comet nuclei fall into this scheme? And as a fourth classification scheme, formation scenarios, where we look at the origin of the solar system and various mechanisms that might assemble these small bodies and lead to the time and place of formation, whether we believe that they are still in their original places, or whether they've migrated to their current location. All are very important for this discussion. Next slide, please. So coming back to the question, are centaurs comets? Well, looking at the pros, of course, I mean, we have already classified several centaurs as comets, but as I've mentioned in the previous slides, is this really enough to make a solid determination? Are centaurs comets as we know them, or could they be some type of a proto-comet leading into the short period or long period comets come into the inner solar system? Could some be dwarf planets, some of the larger centaurs? Could they have differentiated nuclei, shapes? All of these are kind of open questions that bear on this identification of comets as centaurs as comets. As has been noted yesterday, they seem to be intermediary state between KBOs and short period comets dynamically. And as Luke pointed out, reminded us all of this paper that said that centaurs likely have been short period comets, are in the near future maybe short period comets, and then may jump back to their zone of the solar system. So that raises some very interesting kind of exciting possibilities. Water ice has been noted on the surface of these. The colors spectra have similarities. And the large centaurs, as we've seen in the last few talks and yesterday, have CO detections, CN has been detected, some gaseous species, and dust activity. I'd also like to talk a little bit about the size of comets. Is there an upper size limit for comet nuclei? And could it be that the larger centaurs are transitional objects between the smaller comet nuclei as we know today and larger bodies like icy satellites? Okay, and as broadening the question even further, what about relations to asteroids? Is there a compositional continuum between the asteroids and comets? These are all interesting questions that I think need to be addressed. Next slide, please.
2 minutes.
Okay. Centaurs orbit in this unique part of the solar system. It's been pointed out, the inner solar system, where we have water turning on, the outer planetary system, where we find centaurs, where CO2 turns on, and then the trans-Neptunian region, where we have the supervolatiles like CO and methane sublimation. Here's a plot by Stern, by Allen, back in the late 80s that illustrate this point of for Chiron turning on, particularly around perihelion for CO2. So what are the changes that occur to these bodies as they're transiting through this region? Let's go to the next slide. What about the upper size limit for comet nuclei? As we know of comets today, they have unbound atmospheres, extensive exospheres. So we can look at this very simply, back of the envelope type calculations as a thermal escape, using a Jeans parameter, which is basically just the gravitational potential energy divided by the thermal energy of the gas molecules. We find typical comets have this Jeans parameter less than about 1/1000th. Hale-Bopp have one of the larger ones, and many much lower than that. Chiron, if we assume a comet-like density, gets up to about ranging from about 0.07 to 0.23. You can see the numbers for CO2 also. We generally think of a lambda of 2 as a boundary between the extensive exospheres and on the other side, the larger lambdas being the bound atmospheres. You can see that if we look at Chiron more as a more dense object, larger object having density more like an asteroid, we can get numbers approaching 1, and Charlecot can actually get close to 2 if we push the density up looking at CO. As examples, we can see Moon, Mercury, Earth, Jupiter. Okay, we can also think of a collision zone. Typical comets can have large collision zones. This is a region near the nucleus where the gases are collisionally coupled. Chiron, we can see, has a collision zone of about 1,300 kilometers, which is very similar to comets. Bound dust combing rings, all interesting points to discuss. So we can think of the centaurs with these lambda parameters being much higher than comets, but lower than the planets, again, as being some kind of transition objects due to their sizes. Let's go to the next slide.
0 minutes.
Okay, I'll quickly go through this one then. We did a model about dusty gas dynamics. Here we show in the lower left-hand corner, we have temperatures plotted for the gas and dust that are escaping from the nucleus of Chiron, where we have dusty flows, a chi of 1, gas to dust ratio. We see that this heats the gas. And if you look at the figure on the other side, you can see that the result is an increased gas velocity, which is significantly higher than the non-dust case. That would be the upper curve for the high dust velocity. Let's go to the next slide. Okay, activity mechanisms. Some of these have been discussed before. I just note a few that might be operating for Centaurs. A model of mass wasting from sloped terrains, where we can have wet and dry outbursts, the pressurized pores, where we have pressure building up below the surface, which releases, which results in a explosive release of gas, dust. Other collisions, clathrates, amorphous water ice, I believe could only happen very near Jupiter because of the temperature needed to initiate the phase change. Let's go to the next slide, which is my next to the last, I believe. Yeah, just wanted to mention what are some of the motivations for spacecraft missions. So I've listed what I believe might be important topics to address if one were writing a proposal for a spacecraft mission. Many of these I highlighted earlier in the talk. And of course, pointing out the previous missions to small bodies, where exactly a Centaur mission would fit in there. And then my last slide are just the open questions. So these are some that might stimulate further discussion, and I'll go ahead and end on that. Thanks for your attention.
Thank you. All right, great provocative questions about size, especially. Let's start with questions directly for Dan, and we can transition into general discussion. Gerbs? Yeah, here you go.
Okay, so I'm going to wax a little philosophical on the definition of a comet. One thing that is clear with a comet that with the current definition is that it is clear. I mean, it's if it shows if it's extended, if it shows a coma, it's a comet, and if it doesn't, it's not. And then if you open the can of worms of redefining, then you're talking about what's an asteroid, right? And asteroid means star-like, right? So technically, is something that's extended. I mean, there are all sorts of if we start getting into definitions, shifting the definitions. It's an interesting question, but I do see the virtue in kind of clear definition of a comet.
Well,
that wasn't much of a question. I'm sorry. But what would you have to say to that?
Yeah, it's an interesting comment, and I've heard that comment many times before. And I don't think it means that we have to throw out the basis that we use today, but just to expand that and to allow for different, pigeonholes or different compartments within that. As my first slide showed, the etching, we could say that was a comet.
Henry Shea, PSI. So I'm actually not going to comment on that, even though I feel like some people feel like I will. But I will agree with Dan in that it's complicated because it mixes colloquial definitions and historical definitions and scientific definitions. So, but I want to ask Dan, since you talked about it for like 10 seconds, about spacecraft missions. Do you have comments on whether, like, what kind of mission you think would be maybe most productive? Like visiting several centaurs? Is that like possible, like trajectory wise, or like just, you know, going into orbit around one centaur? Like, what do you have thoughts on that? Maybe to give you an extra couple minutes to talk about this since you didn't get to it in the main talk.
Okay, well, I don't really have a strong opinion about the type of mission. However, you know, usually we start with reconnaissance as our first primary goal, to just get flyby missions. And so sampling a few centaurs would certainly fulfill that. And then we move on to orbiters. But I think with the technology we have today, why can't we skip the reconnaissance mission and go right to an orbiter where we can really look in detail at a centaur? And but again, I don't have any real strong feeling on that one way or another. And I did talk with Henry at an IAU meeting a few years back in Beijing. So I have already gone through this discussion with Henry before.
Let's thank Dan again. And now we can have open discussion about questions, especially if they relate to composition, as we've had in this session. Gal?
Thank you. Gus Reed, FSI, UCF. Curbs, I have a question for a figure that you showed, the CO plus CO2 over dust for the Jupiter family, or inward of 4AU and out of 4AU. Maybe I missed it, but is there any information, or can you comment on any information with regards to size with that distribution of CO2 over dust?
So no, those are not scaled at all with respect to size, just with respect to productions.
But do we have sizes for these objects?
Yes, for some of them, yes.
And do you know if there's any trend with size that mucks up this very nice?
Is there a particular size that?
Is there a dependency of size? Does the effective size bring in a different kind of trend to that very nice?
Let's
pass it over.
Yes, sir.
So I have not investigated that trend, but in terms of, I guess one way to put this is that I'm wondering if the scale with respect to the dust production how that would scale as well. So in some sense, has that been taken out because of the actual dust production? I don't know. It's but no, there's been no scaling with respect to the size of the objects, even for the subset that we have actual nucleus sizes for. That'd be an interesting thing to do, though. Yeah.
Matthew Knight, University of Maryland. So this kind of off of what you all were talking about, but really from the lambda genes parameter that Dan just showed, I was just wondering, I've never really thought about the fact that these are much more massive objects than comets. So there's more gravity. It presumably is harder to launch things to escape velocity. So how might that affect our perceptions of like dust to gas ratios and things like that? Has anybody thought about that?
Yeah, Alan Stern Southwest. So they have 10 times bigger diameters. So they have 10 times more gravity, but it's 10 times a tiny amount, right? So the typical outflow speeds of Comets, as you know, are of order a kilometer per second. And the escape speeds from even a fairly big Centaur, like 29P, you know, is of order a few tens of meters per second, depending on what you think the density is. And so they're still going to work the same way a little comet's going to work. They're going to lift those grains and footballs and boulders right off, and they're going to escape. You know, when you get up to very much larger things, like dwarf planets, you'll find that they're going to be bound. And then things are going to work like on Pluto, where you find extreme volatiles like CO and nitrogen that have been retained over billions of years. But for these guys, I think they're just going to operate like mega comets. Go ahead.
No, I just have a question to that.
Yeah, go ahead.
So, but between like a 10-kilometer diameter comet and a 200-kilometer Chariclo, for example. There will be different stable or semi-stable orbits for particles that are launched at or just at the escape velocity at different altitudes and latitudes. Yes. So there will be a different occupation of this kind of cloud around these.
There's only a very narrow range of speeds.
Yeah.
That result in being slow enough to get in orbit and then not being so fast that they escape. It's only one factor of square root of 2.
Yeah.
And you also have to have the angular momentum.
Yeah.
That's simply have the outflow velocity. Yeah. So it's hard. I did a paper with some 3D simulations of this for Chiron back around the time of the perihelion in the 90s. And it's very inefficient. And for an inanimate object, it's not like a launch vehicle, actually got a guidance system aiming to get into it. If you're just throwing particles randomly out, very, very few get into it, unless you have some special processes. So if you have satellites that help, for example, that's different. We didn't simulate it.
Okay.
Did you count for rotation of the body? You did.
I guess that was a related question. What if you have a very elongated body? Do you, because I think that if you're launching particles, but because of your very variable gravity field, maybe it's easier to trap the particle. Did you try some of that? Or?
We didn't. We were interested in Chiron. And
yeah.
We assumed
it was okay.
So we treated it like a point mass from that perspective, just with a finite radius to launch off of.
Okay. Okay, and also, I said that before. I feel like if you launch in the plane of the equator, you already have higher chances than if you launch isotropically. And then with the low gravity levels, if you launch isotropically, you have a more tendency of losing stuff. But okay, we're back at the ring discussion. I don't want
to. Yes, I have a comment on Matthew Knight's question. I did a couple of calculations I didn't put in the presentation of escape velocity from Chiron. If we look at a density more comet-like, say 5 grams per cubic centimeter, we get an escape velocity of a little over 50 meters per second. And that's much lower than the typical thermal speeds at perihelion or even aphelion, which are in the hundreds, 200 to 100 meters per second. However, if we look at Chiron with a density of 2, we get an escape velocity of a little over 100 meters per second. Now we have escape velocities that are comparable to the thermal velocities. So that is going to introduce some gravitational effects if Chiron has that higher density. And it should, of course, these are just back of the envelope calculations, but probably warrants further study of the gravitational effects that are starting to be introduced into small bodies when we hit the sizes of a Chiron-like object.
And Bauer, UMD. There is also, of course, the papers by Belton and I think Nietzsche regarding the possibility of dust exospheres around these bodies. And I don't know about sunflower orbits and whether those would be stable, but those were postulated, I think, for MU69. Yeah, Kelsey.
Charles Shambo, University of Central Florida. I had a question about Casper's, one of his plots, I guess, where they have the CO outburst and the dust outburst. And I guess I don't know if Casper's still online or not, but if not, we can just kind of generally talk about it. But a question about the driver for the outburst or the dust outburst, like it was very interesting when I first saw the plots of like the kind of separation in time between like a CO outburst and a dust outburst. And it made me wondering, like, could potentially there's like just this ongoing like quiescent CO activity that has like fluctuations, and we're seeing kind of a fluctuation in the CO outburst. And it just so happens like there's some service like process that happens that allows like certain dust, like a regolith or something, actually being trained in the dust. So the CO variation isn't really there much. It's just kind of the access to the dust grains to actually be lifted from the surface. Like something happens, is that potentially like, I mean, that's potentially an idea, but like how plausible is that for a scenario? Because like we're not seeing like the dust activity variations are an outburst of like many orders of magnitude. And like the CO variation we saw is like just twice. It's not really as large of an outburst. And it's just, we're not capturing like most of the CO production, or is it like, what's the mechanism kind of?
He is, but his microphone's not connected right now. I messaged him to see if he wants to go with the I hear back on. I can answer.
Okay.
I think you were asking about the variability of the CO production rate.
Yeah.
And was it, but what was the last part that you
Like,
said?
is it enough to drive the variability in dust activity?
Okay.
Variability is so large, and like the CO activity we're seeing is twice or maybe an order of magnitude larger. Is that enough to really drive it, or we're just not capturing? We're capturing the tail end of like an outburst.
Well, I don't think we have enough of the data to tell whether we're capturing the tail end of another outburst yet. Casper does have more data that he didn't talk about here because it wasn't enough time. So we have about double the amount of data. That's a great question. We do see variability in the behavior of the CO production over short time periods, like over half an hour. And I'm not sure we have the data in the optical to go along with that. Maybe Laura will have that with her Great Basin eventually. That's one reason why we're teaming up with her. But it's also good to ask the bigger question is, what do the models say about these processes? Should they be tied together? Could they be leaking out? The gas and the dust could be coming out separately. So.
Yeah, because like with 67 feet, there were
Yes.
like gas outbursts, dust outbursts, gas and dust. There was different types of outbursts they detected. Is 29 PI all outbursts like dust and gas, or are we seeing multiple phases or types of outbursts? I guess. And like, it'd be interesting to have like we don't know, but like what will we need for like observing to actually detect that? Like, what kind of like modalities of observation are they? Kind of coordinated efforts of the millimeter wave to like dust, and then do we get some type of like dust grain size distribution? What will we need for that?
Yeah, and not only a variety in the dust in the outburst at 67P, but also just the outgassing was different. At least the optical brightness, the optically bright dust was better correlated with water production, with just the structure on the as seen on the plane of the sky from Rosetta. Dust was better correlated with water than it was with carbon dioxide and carbon monoxide, those being more tied to the southern hemisphere. Of course, this changes with season, but at least for some of the papers that I remember from, I think they're pre-perihelion papers, not a lot of dust was correlated with those carbon dioxide and carbon monoxide active regions on the southern hemisphere at that time, pre-southern summer. So some of that could be because the fluxes, just the gas production rate's not enough to lift. This is a guess from me. It's not enough to lift maybe enough dust to see with that water active dust coma dominating. But I don't know. It's an interesting point to me. How does carbon dioxide ever lift material other than at Hartley 2, where it seems to be lifting everything off the nucleus? Okay, is that the only exception, or could that be generalized?
I'll go back for a second for about the question of the dynamics of particles lifted off the surface, and for just 1 second, I'll put Jenny Larson on the spot, because her thesis project is developing an n-body ejecta dynamics model that takes into account rotation, multiplicity in a system, so binaries, satellites, etc., ellipsoidal shape, and a size distribution for the particles. She's applying that to the DART mission, but in essence, any environment that lifts off particles off a body is viable for that. And so this question of what kind of orbits these particles can take, for how long, how stable will it be, but also to the question of, is it a dusty outburst? Is it a dusty gassy outburst? It's a mostly gassy outburst. If we involve a size frequency distribution of the particles of dust that are lifted, there is a distance above the surface where the gas and the dust particles are still coupled or semi-coupled, and a size distribution for the particles will actually affect the final trajectories of these, not the final, sorry, the intermediate trajectories of these particles in that system. Gas track. Did I put you enough on the spot, Jenny? Okay, good. Someone else then, please.
More things about carbon dioxide. Let me have a question. I'll ask a question. We talk about, we've had several notions about this amorphous water-ice transition and it being a progenitor for activity. But isn't this the same regime where CO2 can still be active? And at which heliocentric distance? And we talk about water ice line, and we know that's kind of a phony concept, but it does mark a location where water production or water volatility decreases when you go farther out. And that happens for CO2. And I thought that for CO2, it was around 10 or 12 AU or 6. Okay, even closer, yeah.
Oops, I'm sorry. Okay, so if you take 3 as the distance for the snow line, or the inner area of the snow line, if you want 4, whatever, then it's 6 to 8 for the CO2 or something like that, and then you can scale it relative to the Z production plots if you want. Yeah.
Okay. Back to go.
Thank you. So the idea for the amorphous crystalline transition is, I'm just now talking purely as stupid modeler. The idea is you want to put something in your calculation that holds very volatile molecules for dear life. So if you're seeing CO at an environment that has an effective temperature, which is much higher than the volatility temperature, the sublimation temperature of CO, you want to have something that will keep it there for as long as you need it. You can try different numerical tricks. The one that has correlation with an existing material in the lab is amorphous ice, with its ability to trap very volatile material, as shown by the group of Akiva Barnoun, the late Akiva Barnoun in Tel Aviv University. They've shown that. Since then, several other groups have shown the capacity for amorphous ice to trap very volatile material, CO, nitrogen, argon, etc. And so that is essentially a good trick to do that. But as we've heard, I think yesterday, we don't have evidence for amorphous ice on the surface of any object. And so right now it is still a very useful trick or a very useful mechanism to apply. The transition of amorphous to crystalline ice is also not extremely clear. A lot of us use a continuous function for that, temperature-dependent continuous function. How true is that? It depends on experiments that were done a while ago and have not been repeated or been sparsely repeated. The idea of, is it exothermic or endothermic, as Jordan told us, is again not very clear. It depends on the contaminant level of the amorphous ice. And so it's a mechanism that there are opinions. I mean, Rosetta, there's a team of Rosetta-related scientists who claim they can prove there's no amorphous ice on 67P. But it it's very dependent on the way they model the activity that they measure on 67P. Yeah. Yes, please. There is lab work, but some of it is very old and has not been properly repeated since. For example, the transition from exothermic to endothermic reaction in the crystallization process that has not been clearly repeated.
And when you say they're claiming that they see no amorphous for sure on 67P, is it because they have that one signature structurally every time?
Yes, they also claim that their model that tries to reproduce some of the activity in a certain region on 67P doesn't seem to correlate with using amorphous ice as a subsurface driver for the volatile activity. But that's very dependent on the way they implement their model. It's not evidence.
Just have a small comment because the amorphous crystalline thing reminds me a lot of sort of the ammonia detection stuff for even farther out, that we always assume it's there, but we didn't see it. We did see some, not a lot. But we've been having discussions about what new lab work is needed for that, and including, destruction and creation processes, both, to see, do we really, are we correct about what we think about how to get rid of it? And are we correct about how to get it back on the surface?
I'm just sorry. This is for you guys. How much energy are we talking about when amorphous ice goes back to a lattice? So it gives out a certain amount of it gives out a certain amount of energy per time. And how much are we talking about? Did you guys look like, is that something that could lift significant amounts of dust?
That's something that can depends on your model. It can lead. There are some models that turn it out to lead to a catastrophic explosion in an ice body.
I see.
Yeah, there's a chance that you could cause the entire object to really detonate and explode.
Because
common homes.
So because you're heating, you build up vapor in there and then it explodes, or
the issue is that relatively pure amorphous water.
Oh, I'm sorry.
Jordan Steckloff, PSI. So the argument is that relatively pure amorphous water ice, when the molecules, the lowest energy state for the molecules in a crystal is to be in the crystal lattice. And so when you're in this glassy phase, it's actually a higher energy state. And so when the molecules diffuse into a lattice site, they actually release energy. And so the argument would be, and it's a significant amount, especially for water, that this exothermic phase transition could potentially trigger a cascade of phase transitions for all of the amorphous water ice, and you release all of this energy, and next thing you know, the entire thing explodes. So the argument could be that it is. The timescales are highly temperature dependent because you can think of it as a diffusive process. And so warmer temperature, things are moving faster. You might be able to diffuse. You could go.
It's an exponential dependence on the
right.
You can move between relatively close by heliocentric distances.
Yeah.
Oh, sorry.
Yes.
By the way, it's way better.
Me or the microphone? What we take right now as the rate of the crystallization process is dependent on the temperature in an exponential fashion. So you can move between relatively close heliocentric distances, and it can take you years to crystallize amorphous ice versus minutes.
Wouldn't you see then in the distribution of activity with heliocentric distance, would you see that?
I guess that's a framing question for these 2.5 days.
So Jordan Steckloff, PSI. So Dave Jewett has a 2009 paper where he actually looked at that and is arguing that the heliocentric dependence of the activity that is observed for the active centaurs is consistent with the amorphous water ice crystallizing and releasing these gases. And the argument he was looking at, I think, was supervolatiles CO or CO2. and trying to explain that, look, if because he was trying, the one of the alternatives is that, well, what if you just have a block of carbon monoxide ice? And it's incredibly volatile. And the thought would be that it would be highly unstable, and we should see it sublimating out in the Kuiper belt. Now, I'm sure that there's certainly ways you could have a structure that protects it. Maybe it's in the interior, or it's in a permanently shadowed region, or whatnot. You know, there's ways of protecting it. But if we just take two basic models where you have a ball of CO and you have a ball of amorphous water ice with some CO in it, the observations are more consistent with the ball of amorphous water ice with CO than it is with a ball of CO. And so that's what that paper would be arguing. And obviously the caveat is that these are model dependent and both could be wrong. Jewett 2009.
Thanks.
Mm-hmm.
So numbers, just kind of numbers. So let's see, water crystallization is enthalpy, specific enthalpy is kind of like the enthalpy you get for water melting. So it's I mean, if it's exothermic, it releases that amount of energy. So it's a pretty strong process, but it has to be triggered, right? We don't need to trigger solar radiation. We need to trigger radioactive decay. This is a process that needs some sort of input to start working, which can relate to why things seem to be inactive, and then they cross a certain threshold, and they seem to all of a sudden show activity. It's another, like sublimation, it's a process that needs triggering. Unlike sublimation, this is a process that can be triggered and then can be self-sustained, at least for a while.
All right, online for the final.
Yeah, Dan has a question too. You have the floor right now.
Oh, okay. Yeah, thanks for recognizing me. I have a couple of comments and a question about the amorphous water ice. One thing to keep in mind, amorphous water ice has a density over 2 grams per cubic centimeter, 2.3 or so. So when that phase transition actually occurs, you're going to densities of about 0.9 something for the crystalline lattice. So there's a huge change of volume that occurs, which is part of this explosive energy release. And I can understand from the experiments by Barnoon and others about the trapping of the supervolatiles and the release when the phase transition occurs. But my question is, I'm not clear, is there also a release of water during that phase transition?
Okay, Jordan Steckliff, PSI. So there's actually, the one thing we need to keep in mind is that there's actually multiple phases of amorphous water ice. There's low density amorphous water ice, high density amorphous water ice, and very high density amorphous water ice. And I'm waiting for someone to find overwhelmingly dense, ludicrously dense amorphous water ice. So we have these three, and low density amorphous water ice is actually comparable in density to crystalline water ice, ice 1. And so there's not, you don't necessarily have a very large change in density. It could be relatively small. We could have, from a transition from one form of amorphous water ice to a lower density form of amorphous water ice, there might be some interesting effects. Now to the question of, is there going to be water, I'm sorry, I'm assuming the question is, do we have water vapor being associated with these crystallization events? And I think the argument would be it depends on at what temperature this occurs and at how energetic the phase transition is. The general thought is no, I wouldn't necessarily expect it, just because we're dealing with temperatures of 120 to 150 Kelvin or so. It's still incredibly cold, but you may see something. It could be kind of a splashy process.
Sorry, I'm back at it. Sorry, I said I would stop it. So does it play a role if you had, like, would you need a big block of that water ice to be proceeding in that way, or would it be very different if you had just a multitude of grains of that water ice? Like, what if you have a bunch of grains and they're mixed with dust grains, for example, would you also get that accumulation of energy that will lead to the explosion?
So that's an interesting caveat, and the thought would be that if you have effectively non-explosive material, if you have dust mixed in with amorphous water ice, if you trigger the phase transition, and even if it is a highly exothermic process, you might be sending so much heat into the dust that you can actually quench it. I mean, so we can think of one extreme where it's almost pure dust with a little bit of amorphous water ice. You crystallize the ice and nothing really happens because the dust absorbs most of that heat. On the other hand, if it's mostly amorphous water ice with a little bit of dust, then I would think that, okay, so the dust warms up, but it's a small part of the energetics of the whole process. And so I think it would really depend on structures and concentrations and porosity and granularity.
Yeah, okay, let's finish. Yeah, all right. So thank you for great, excellent discussion. And we have a break scheduled from now until 3:30. So let's do 3:30.